Welcome back to the next video, everybody. Today's video will be on Devissage and Raynaud F-module schemes. Devissage is an all-encompassing term that usually just means if I have an exact sequence of objects and two of the three objects satisfy some property, then the third one does as well. Okay, so we're going to apply that here and see what we can figure out about prolongations. So let's let 0 to G prime 0 to G 0 to G double prime 0 to 0 be an exact sequence of finite K group schemes where K is a field of characteristics 0. And we will let A double prime 0 inject into A0, which maps to A prime 0, be the corresponding K algebra setup in the reverse order. So reverse the order here of the arrows and take the corresponding K algebras. We talked about this last video. Okay, let's suppose G equals spec A prolongs G0. So you can view G as just living up here. Okay, so let's let A prime be the image of A and A prime 0. So we have G up here corresponding to A down here. We can look at the image A prime and A prime 0 of A, and then we can set G prime equal to spec A prime, which lives up here maybe. And maybe you suspect this prolongs G prime 0, right? Now, incidentally, G prime is the scheme theoretic closure of G prime 0 and G. And yes, it is easy to see that G prime is a closed subgroup scheme of G that prolongs G prime 0 as expected. In fact, it's the unique such object with the property that the inclusion G prime in G extends the given map from G prime to G0. All right. And then what do you hope happens? You hope that if you take G mod G prime, and we'll call that G double prime, that the result sits up here and maybe prolongs G double prime sub 0, and that happens. Okay, so we have that. We have a Devissage of prolongations, I guess. Okay, so let's look at some basic properties of prolongations with respect to this whole Devissage thing. So basically, induction plus the above discussion allows you to prove the following, which is done on CSS page 147. This is called proposition 6 in my notes. We'll let G be a prolongation of a fixed finite K group scheme G0, and we'll take a composition series for G0, and we'll call that series G to the J sub 0, where J runs from 0 to n. So we're taking G0, we're thinking of it as like G0 to the n, and we're taking a chain of simple finite subgroup schemes of it in descending order. That's what's going on here. It's the same thing as a composition series from your algebra class. Okay, then two things are true. There are unique prolongations, which we'll call G to the J, of the G to the J sub 0s, such that the inclusions that we have that were given by the definition of composition series, G to the J sub 0 and G to the J plus 1 sub 0, induced closed immersions on the level of prolongations. So I'll get closed immersions from G to the J to G to the J plus 1. And then quotients and prolongations play well with each other. The quotient of the prolongations given by G to the J plus 1 mod G to the J is a those are prolongations of the quotients of group schemes G to the J plus 1 sub 0 mod G to the J sub 0 for all J. And so the quotient of the prolongations is a prolongation of the quotient, in other words. Okay, let's suppose I have another prolongation H of G0, and suppose I know H is a subgroup of G. Well, then it turns out that taking quotients kind of respects this subgroup inequality here. So G to the J plus 1 mod G to the J, that contains in it as a subgroup H to the J plus 1 mod H to the J for all J. And if you happen to have that this inequality here, this subgroup inequality is an equality for each J, then it must have been the case that G equals H to begin with. G must have just been the same thing as H to begin with. There was a uniqueness of prolongation there. Okay, and pay attention to uniqueness of prolongation because we're going to be talking about it more in the next couple of videos. Okay, the last thing I want to talk about today is F-module schemes and F-module Raynaud schemes. We'll let K bar be an algebraic closure of K, and we'll set like cal G equal to the absolute Galois group of K. We'll let G be a finite flat commutative R group scheme for some R. Since we recall that the characteristic of K is assumed to be 0 throughout all this, the generic fiber G0, which is G base change to K, is just determined by the cal G module G0, the K bar points of G0 or the K bar points of G. Okay, this is generic algebraic geometry here. Let's call G simple if G0 is simple. G will be simple if G K bar is a simple cal G module. So as a Galois module, it's just simple, okay? Which is to say, I mean, what's a simple module if you don't know that definition? It's just a module with no non-zero proper submodules, okay? So what is an F module scheme? Let's let F be a ring with unity. An F module scheme over a base scheme S is just a commutative S group scheme, G, let's say, together with a unital ring homomorphism from F to NG. I mean, it's exactly what you think it's going to be, right? It's a group scheme that's an F module, basically, in the only way you could possibly define that. Now, notice this, and maybe an even nicer way of thinking about this is that this setup makes G of T into an F module in the ordinary sense for every S scheme T, and this is functorial on T. And the upshot of all this is that an F module scheme is just the same thing as a representable functor from schemes over S to the category of F modules, which is how I think of it personally. If you can think of things in terms of functors, it's usually just easier and nicer to do that. Okay. So what's a Raynaud F module scheme then? Well, if F is a finite field, so let's say we're playing this game over a finite field F, then a finite flat F module scheme that has the same order as F as a group scheme, which we defined many videos ago, that's just called a Raynaud F module group scheme. Okay, so that's we defined the order of a group scheme quite a while ago. It has to do with the structure sheaf of the scheme and kind of its rank as a locally free sheaf. Okay, so proposition 7, which will end the video, we'll let G0 be a simple commutative K group scheme of P power order for some prime P, and we'll assume that prolongs to some G. We'll assume R is strictly Henselian, or more generally, let's just assume that cal G acts on the K bar points of G that factoring through an abelian quotient group. That's all we really care about. Then F, which I will define to be the endomorphisms of G0, which incidentally are also the endomorphisms of G plus and G minus, where G plus and G minus are the sup and the inf under the ordering that we put on prolongations last video. That's a finite field. And so what we find actually is that G0, G plus, and G minus are actually Raynaud F module schemes under this setup. And so for a proof of this, you can see CSS page 148. And we will use this to finally start getting to Raynaud's 2 major results that we need for the proof of Fermat's last theorem, beginning, I believe, next video. So I'll see you then, and thanks for watching.